Bienvenue à tous à ce deuxième événement de la série Perpertive Quantum, donc qui porte sur différentes technologies quantiques. Toute cette série est présentée en collaboration par le COPL, Centre d'optique photonique laser, INTRIQ, Institut transdisciplinaire d'information quantique, Optonics, ISEQ et NUMANA. Donc, je me présente, Nicolas Godbout, je suis professeur au département de génie physique à Polytechnique Montréal et directeur de l'INTRIQ, l'Institut transdisciplinaire d'information quantique. Il me fait énormément plaisir d'accueillir aujourd'hui notre conférencier, Yoann Jestin, qui va nous parler de sa startup, Key3 Photonics. Donc, Key3, pour des gens qui ont fait de l'optique non linéaire comme moi, Key3, ça évoque justement ce domaine-là, ce domaine d'optique non linéaire, puis il va nous parler donc d'applications quantiques. Donc, Yoann est cofondateur et CEO de Key3 Photonics, qui est une entreprise dérivée de l'INRS, l'Institut national de recherche scientifique, la division énergie, matériaux, télécom près de Montréal ici. Donc, Yoann va nous faire une présentation en anglais aujourd'hui, mais on vous invite à poser les questions en français ou en anglais. Pour les questions, vous pouvez à tout moment écrire vos questions dans le chat. Donc, vous avez un onglet là, sur la droite de votre fenêtre où vous pouvez poser vos questions. Et donc, je vais relayer les questions à Yoann, soit à certains points durant la présentation, à la toute fin de la présentation. Aussi, on va vous inviter, tout le monde, Yoann et tous les participants, à rester sur la plateforme Remo à la toute fin, lorsque nous aurons fini la présentation à la période de questions. Nous allons retourner dans l'espace, donc l'espace de conférence avec les tables et vous pourrez encore discuter entre vous ou discuter, poser plus de questions à notre conférencier, Yoann. Donc, et aussi, nous avons une table spécifiquement pour INTRIQ. Et le coordonnateur d'INTRIQ, Marc Leclerc, sera là aussi pour répondre à des questions. Si vous avez des questions sur tout l'écosystème dont les technologies quantiques au Québec ou sur les différents appels à projets du ministère de l'Économie et de l'Innovation, il pourra vous répondre à des questions sur différents sujets de la sorte. Donc, alors sans plus tarder, je vais céder la parole à Yoann pour nous présenter donc sa startup Key3 Photonics. Yoann.
Merci beaucoup Nicolas pour l'introduction et puis je voudrais remercier l'INTRIQ, Optonics, ISEQ, NUMANA, le COPL de m'avoir donné l'opportunité de présenter ce que fait Key3 Photonics. Donc je vais essayer de partager mon écran. Alors, attendez, je vais peut-être avoir un peu de... Est-ce que vous m'entendez bien?
Oui, très bien. On voit bien la présentation.
Okay, perfect. Donc, so I'm going to start the presentation on English. I think it's more international, especially when we talk about quantum and science. Sometimes there are some words that are not even coming to me in French. So we're going to do it international, but I can answer a question in French or in English. So there's no problem. So yeah, today quantum technologies are really omnipresent in the media. Quantum computers, quantum sensors, quantum communications, and today companies that are looking to enter or explore this space spend on average on a 5-year quantum project, 3 years on equipment sourcing and customization, 1 year on checkdown, and only 1 year actually doing the work. So it's really urgent to support such company with a strong quantum supply chain. And furthermore, supporting the quantum supply chain in the field of photonics with adapted instrument will also enable the development of versatile quantum communications. So hello everyone again, my name is Yoann Jestin. I'm the president and co-founder of Key3 Photonics Technologies. And our mission is really to enable the development of all optical quantum technologies. So Cryptography Photonics is the university spin-off that I co-founded with 3 colleagues from the Nonlinear Photonics Research Group of Professor Morandotti. So we founded the company in 2015. We started kind of slowly because we were all scientists and involved at the university. And since a bit now more than 5 years, we are basically developing quantum photonic hardware. And that is coming directly from innovations that have been realized in the lab for more fundamental quantum research, let's say. And our initial vision was really to try to position ourselves as a first quantum OEM on the market. So displaying quantum instruments for people that want to do quantum. And we'll see later that this vision has evolved a little bit in order to be closer to the reality of the market. So you're not going to learn anything if I'm telling you that quantum technologies are really booming. And there's a lot of companies that are racing to build the first quantum computers. So we can cite Microsoft, Google, Honeywell, but also less fortunate company like startups, even if some of them are already raised hundreds of millions of dollars. So here we can see INTRIQ, PsiQuantum, D-Wave, Xanadu that are based in Canada. And one common thing that those companies are facing with when working in the field of quantum is that the instrumentation is very complex. And most of the systems that they are using are very unstable because the qubits are by definition unstable. And this happens that this instrumentation is very costly. So there is actually a need to also adapt to the current infrastructure, like, for example, the optical fibers that we are using every day to communicate. So it's really urgent to adapt everything and to have quantum instruments that can be used by everybody and then can adapt to our current technology. So what Cryptography Photonics initially proposed is really to provide photonics hardware for the generation and manipulation of non-classical photons. And with a particular emphasis on the compatibility with the existing optical fiber network, but also we're trying to focus on building simple instruments that require low maintenance and that going to have a compact footprint in order to not to be, for example, in a big room with a refrigerator, like we can see, for example, with quantum computers. So in this sense, we can target different quantum markets, like the one, for example, for quantum secure communication, in particular through the development of quantum cryptographic key distribution, which is looking for solutions that can adapt to the classical optical channels. And this basically represents a market of $167 billion, even if the numbers are always changing and there's a kind of estimation. So these are big markets. There is also the quantum sensing market that intend to use quantum technology to beat the actual limits of our sensing instruments. And also the quantum computing market that is, a lot of people are talking about that, which represent $450 billion. And in this case, even if we are not going to use a photonic computer and there are different type of technologies, those computers at a certain point, they're going to have to communicate to each other, and we'll probably going to have to use the optical existing fiber network, or at least communication network, in order to make them communicate. So that's why, as I said, there's a lot of opportunities in the quantum space, but I'd like to talk a little bit more now on quantum communication, because this is where we are focusing now, kind of the first market we're trying to focus, and how the threat of quantum computers is pushing toward a fast development of quantum communications like quantum key distribution. So to put the thing into context, I'd like to give you some numbers on the critical data that are stolen during the cyber attacks. So SIV steal data constantly, so protecting it is really an ongoing challenge. And there are more than 6,000 banks with 80,000 branches in the United States, for example, nearly 6,000 hospitals and thousands of insurance companies, all with data that have to be kept private. And from what we read from a recent report from IBM, mentioned that the average total cost of data breach is estimated at $3.92 million, while the average time to solve it is close to 9 months. So today, this is the United States that has the highest cost of data breach, and the healthcare industry is the most affected. And of course, the percentage of chance of experiencing a data breach is increasing over time. And today, you're basically more likely to experience a data breach of at least 10,000 records. So according to IBM, in 2019, it's 29.6%. So you have more chance to experience a data breach that you have to catch the flu this winter. So, of course, these numbers are rising. So you see in 2014, it was 22.6%, 29.6% in 2019. So it's really important to protect yourself and to find solution against these cyber attacks that we can see every day in the news that someone has been attacked with something. So why this is happening? So this is basically because cryptographic algorithms are now no longer secure. So indeed, there are standard methods for exchanging cryptographic keys are actually in jeopardy. And for example, the famous algorithm RSA 1024 that was once commonly used to exchange keys between browsers and web servers has probably been broken now, and it's no longer regarded as safe by NIST, which is the National Institute of Standard Technology, which is basically regulating all the standards for cryptography and also other things. And while there are other public key infrastructure technologies, perhaps that haven't been broken yet, they will be soon by bigger and faster computers. And once quantum computers are going to become mainstream, so data encrypted using the existing key exchange technology will really become even more vulnerable. So it's really important to act now in order also to protect companies and institutions from the famous, how do you say that, the quantum apocalypse that they're calling that, the data apocalypse, that basically hackers are going to be able to download your data now and maybe decrypt them later. So researchers are actually working on methods to improve the security of software-based key exchange methods using what is called the post-quantum cryptography. So there are basically two schools. There is post-quantum cryptography and quantum key distribution. So post-quantum cryptography is a method that will continue to be effective after quantum computers are powerful enough to break existing key exchange methods. So they are all based on the unprovable assertion that certain numerical algorithms are difficult to reverse. But the question that remains is difficult from whom? So how do we know that an unpublished solution to this exact problem hasn't been discovered yet? And the answer is that we actually don't know. So On the other side, there is quantum cryptography or quantum key distribution, which is the only known method that for transmitting a secret key over long distance that is probably secure in accordance with the well-accepted and many times verified laws that governs the quantum physics. So in this sense, when there are always kind of a debate between post-quantum cryptography and quantum key distribution, saying that quantum key distribution is a hardware solution, but it's too expensive, and post-quantum cryptography will be better because we have a lot of algorithm, and this is going to be sufficient to protect ourselves. But post-quantum cryptography you will always have a doubt, and basically you will always need some periodic updates to remain secure. On the contrary, quantum key distribution that is has a kind of a unlimited lifetime. So it's based on the hardware, so you have to invest at the beginning, but can also be seen as the everlasting security, rather than sometimes we call it the unconditional security. So of course you're going to find loops also in quantum key distributions, but you can protect your hardware in such a way that you're really reducing this holes, let's say. But yeah, quantum key distribution is really the everlasting technology with respect to post-quantum crypto that really is going to have to evolve and get some periodic updates. So how quantum key distribution is working? So it's pretty simple. You can see here on the little drawing on the slides that I have that you have basically two users that are usually named Alice and Bob that are sharing an encoded message through public channels. And there is also a quantum channels, and in the quantum channel they will basically exchange the keys to decode the message. So of course the quantum channel is highly secured because it's quantum, and the classical channel is not secure, but the message is encoded in the classical channel. So quantum key distribution is based on the laws of physics, and it basically protects you from the fact that hackers could download your encrypted data now and decrypt it later when quantum computers will become mainstream. So just to give you a little image, quantum key distribution. So you can use different techniques, single photons, and but also entangled photons. And such photon can be seen, for example, as two particles of light dancing at the same music. And no matter how far they are from each other, so it's going to be distributed to Alice and Bob. So any interaction on one of the particles will have an effect on the other one. So it is this property that is going to be used in order to notify the user of an eventual eavesdropper. So what are the challenge and solution that we propose? So I'd like to mention here the 3C, which is complexity, compatibility, and cost, that I already mentioned a little bit earlier. So quantum instrumentation is usually bulky, complex, and dedicated optical fiber may be required for one-to-one communication. So it's expensive, it's time-consuming to develop QKD networks, and even if test lines are now being deployed around the world, there is an urgent need to adapt the current infrastructure to the existing fiber optic networks. And finally, to date, there are also very limited solutions that can link multiple users. So K3's mission is trying to enable the QKD development by trying to solve these problems. For example, by providing simple instrumentation that can be compatible with telecom standards, but also by having a high flexibility, and that can be integrated with the fiber optic networks. Of course, we are trying to focus also on low cost in order not to have the need to deploy new optical fibers. And we are trying also to focus on the multiplexing technique, which is a combination of multiple signals that can basically connect multiple users. And that is currently used in classical communication, but which is not really used up to date for quantum communications. So what our technology looks like. So here I'm going to mostly talk about generation and manipulation of photons for quantum applications. And in particular, we'll talk about quantum optics, but also optical fibers, optical frequency combs, integrated optics, scalability, flexibility, etc., etc. So if you want to build a quantum channel, for example, for communication and implement it in a network, you will have to generate many quantum states. And there are different ways to do it, but one promising avenue is to generate complex optical states. So here's a fantastic demonstration of complex and multi-photon states, and even families of entangled 4-photon states. But this approach typically relies on polarization and spatial modes. And we can see here that the bulkiness and complexity of the approach makes them very, very difficult to scale up. So it's kind of very complicated, and you cannot adapt this to the optical current network that we have. So one solution that could replace the previous and bulky generation schemes that I showed you is to use optical frequency combs that are basically light source with a broad spectrum of evenly spaced frequency modes. And on chip, so you can have those kind of frequency combs that are generated on chip, and they can be generated by exciting a microcavity resonance, in particular via spontaneous four-wave mixing for K3 materials. So you have several multi-channel sources based on quantum frequency comb that have already been demonstrated with different type of excitation that can be a continuous wavelight or pulsed light. But there is a but, because whether it's continuous or pulsed, you might have a chip, which is the microcavity that you can see here in red on the slide. But you're gonna also have a bulky laser behind it, and so this bulky laser is filtered to excite the single resonance on the microcavity. So for such type of schemes, so it brings, of course, the scaling complexity, and furthermore, the high Q resonances of the microresonators that on the order of 100 megahertz. You have the laser that is basically broader, so there is a large part of the energy that is coming from the laser, but that basically doesn't couple into the microcavity, and that result to be wasted. And finally, there is also a lack of versatility, as many lasers offer limited tunability and versatility of excitation. So yeah, we can see reduced scalability, added complexity. It's not energy efficient to use this kind of laser, and there is a lack of output versatility. So the idea that has been developed into the group of Professor Morandotti and that K3 Photonics is trying to bring to the market was to come up with something more practical. So a practical scheme for the generation of pulsed frequency comb. So we have in this case a larger cavity that is surrounding the microcavity, which has also a smaller free spectral range. The resonance is defined here by a bandpass filter, and with it we have the spectral mode arising from the external cavity, which have their individual phases. And if there is no mode locking element, the relationship between the mode and the phase is random. And this leads to random pulses trained that we can go, this is the chaotic regime. But if we have a modulating element, like the modulator that we can see here in the scheme, which with a frequency corresponding to the spacing of the resonances, there's going to be a fixed phase relation that leads to pulses circulating in the cavity. And pulse excitation of forward mixing in the cavity can occur, and we have, in this case, a mode locked regime. So this is basically a representation of what we have. So we have this microcavity, an amplifier, modulator, a bit of fiber in it. And this is one of the first products that we have. So we already have, of course, the proof of concept. And we are basically now packaging it. So it's basically a quantum source that can generate photons on more than 50 channels. And of course, it's a key element, according to us, to build the future quantum networks, as it can provide a versatile solution for the distribution of keys to different users. So your keys are kind of distributed over the COM, so you can easily see that you can be able to make an efficient information traffic management. And of course, by this already integrates with fiber optics and integrated components, and it does not require the use of bulky external lasers or also nonlinear crystals, but just an optical amplifier and a nonlinear integrated micro-ring cavity. So yeah, just to say that combining integrated chips with fiber optics, we're going to be able also to do multiplexing, and pack our, let's say, quantum signal in only one fiber, and then after distribute it to multiple users. So once you have generated photons with your source, there are multiple degrees of freedoms that you can use to encode quantum information. So we can encode the information into different spatial paths, either on the top of the bottom, also in polarization, which is either horizontal or vertical, in frequency, or simpler into the arrival time, which is the so-called time-being entanglement, which is basically very practical and easily accessible and scalable degree of freedom. It also allows for more complex quantum schemes, such as hyperentanglement or cluster states, where time and frequency encoding is used simultaneously. So the benefits of using these time-being entanglements include the high robustness. It's easily accessible. You have single spatial modes. It's compatible with the standard telecom components. It's scalable to higher dimensions. And you can have the creation of more complex states. So how does it work exactly when you have a time-being entanglement, and how it looks like? So in our case, it starts with a pulse laser, which is delayed by an unbalanced interferometer with a certain phase, theta, which corresponds to a time delay, delta t. So you have a short and a long that correspond to the short and long path of the interferometer. And so after creating those two pulses, which are basically phase locked, they enter into a medium where entangled photons are created, which is, in our case, in the case that I showed previously, it's a nonlinear micro-ring that we use to create photon pairs through spontaneous four-wave mixing. So those photons are created in a superposition of a long and short time, And however, you can already see the problem here that, so sorry, I have to go with the animation. But we require in this case 3 different interferometers for these experiments, and all those interferometers require a stable phase over a long time, since the measurements can take minutes to be done. So the question is, how do we achieve a stable operation of the interferometers as fluctuation of like temperature, acoustic vibration would change the armlets constantly, resulting in a non-constant time varying phase, which would make measurements almost impossible, actually. So as I just mentioned, so yeah, interferometric systems are highly susceptible to external sources of noise, and it requires most of the time an accurate phase tracking or real-time stabilization. So in fact, the sensitivity of interferometer to small perturbation, which makes them ideal tools for metrological application, is detriment when used for coherent signal processing. And it's unintentional perturbation, such as those arising from mechanical, seismic, and thermal effect, couple very easily to an interferometer, bringing about phase drift and instability in interference. So without a proper treatment, this error can reduce interferon contrast and can be seen here in extreme cases to render the interferometers inoperable. So being able to recover and or actively stabilize the interferometer phase thus underpin their operation. So one can try to reduce the amount of environmental noise that couple into the interferometer. And we have, for example, here some pictures of the system of optical suspensions that is used for that purpose. So to kind of isolate the interferometer in the world's best interferometer, which is the LIGO experiments. But even with passive stabilization methods, the phase will drift, and for this active phase recovery and feedback is necessary. So LIGO, for example, uses an internal seismic isolation system to actively adjust for seismic noise. But LIGO is a very, very large system. So what about interferometers that are portable and practical for signal processing? So, of course, different platforms can be used for to build interferometers, but let me focus on the optical fiber platform. So it's a very practical platform toward such device, but stability and full control are still not easily achievable in fiber interferometric system. So the detriments of free space systems that require fragile alignment are quite clear toward them, being used for mass productible device. So moving to fibers gives the benefits of using a market mature platform with minimal losses, but also portability for application that may require out of the lab deployment, but also ease of use. And this is especially important to reduce the barrier of entry to only expert device operators, and compatibility with lasers, telecommunication, and detector infrastructures. So not surprisingly, due to this reason, so the phase recovery and stabilization has been an active research topic in fiber interferometers for about 20 years now, and with very impressive works making use of reference lasers coupled with locking and actively swept arm delays and laser frequencies, as well as system making use of detail. However, the phase recovery schemes either exhibit ambiguities in the reconstruction of the phase, or certain phases are also can be inaccessible for stabilizations. or some of the setups also suffer from high setup complexity and cost. So toward these ends, we have demonstrated a new fiber interferometer and a phase recovery method that is based on quadrature encoding in degrees of freedom that are well suited for inexpensive fiber manipulation and propagation. So here is a brief display of our method in action. So we have the interferometer on the right, and we see its phase being reconstructed in real time. So you could see just before that without stabilization, you can see that the perturbation and the noise coming from the environment is influencing the drift. And if we activate our stabilization system, we are able to, let's say, maintain a stable phase with very high accuracy relative to a reference, and even despite the noise. So we are also able to swap the interferometer to arbitrary phases, and this for hours and hours to have something, the phase of the interferometer that's going to be very, very stable. So here the little description of what we have. So this type of interferometer can be used for, let's say, quantum signal stabilizer against perturbation and environments. So it can provide highly stable temporal encoding. It's also compatible with the fiber existing infrastructure. It has a minimal hardware requirement, and it's also a kind of a low-cost approach. And here is the picture of the stabilization system that we have that is not a prototype anymore because we are already commercializing it. So we sold one unit to a university partner, and we are actually also now testing it with some telecom partners like AT&T that want to integrate those kind of stabilization system coupled with the interferometer into some quantum experiments for teleportation and quantum communication and things like this. So, of course, if you are interested in buying or knowing more about how it works, I could give you more details later. And we could discuss also if you want to use it in your setup and test it for quantum experiments. So just wanted to give you now a little bit more comments on the market and the traction that K3 Photonics is having. So countries and organizations have been developing their own QKD networks since more or less 2004. Which is bringing the global QKD market to something like $20 billion. And even Canada now is moving forward with Xanadu, which is also trying to implement QKD test lines between their headquarters and the University of Toronto. So there is a lot of things going on everywhere. There is kind of this race between US and China. China is really involved in quantum communication. And so a lot of companies and also telecom providers are now trying to implement test line and see how it behaves against attacks and things like this. So we have started to investigate the market, and we have been in touch with university research labs, system providers like Toshiba, that is really pushing a lot on QKD, but also network providers like AT&T in US, British Telecom in UK, Verizon, that are all looking into QKD technology. And we'll soon try to reach end customers also in order to try to put, let's say, pressure on telecom companies, especially in Canada, in order to push them to try to implement QKD networks. So far we have we had a great validation from the contacts that we have. As I said before, we sold one unit of our interferometer and stabilization system to a university research lab. We have agreed with Caltech also and AT&T through the FQNet network that they will test our stabilization system in the QKD testbed, probably during the months of April or May. So this will be very important for us in order to get feedback from potential customers. And also British Telecom also agreed to, so the British Telecom was not that much interested into the interferometer. They were more interested in testing the source in their network as soon as it will be packaged. And finally, there is also Toshiba and Verizon that are basically reviewing our technology internally. And also, there's something that happened actually yesterday. We were also in contact with the US Air Force Research Lab that is working on quantum technology, and the research lab is very interested in the source that we have in order to generate entangled photons on an optical frequency comb, and this is really for communication purpose and deployment of quantum networks. So the market opportunity, so here I can go very briefly on the product that we have. The estimated worldwide QKD revenue would be something like $2 billion. For sources and stabilizer, it can be something like $3 million. No, 200, million dollars. And the estimated market share that Photonics is trying to get is something like $3 million. So there's really high numbers. So here's a little timeline of where we are and where we want to go. So we have been very grateful to the government of Quebec that we have been accepted to some grants with the MEI and Prima Quebec. So we actually have one grant in collaboration with the university, and then one that has been recently accepted in April, and Photonics will be the lead in this case. We will probably go for a financing round around starting in September, as we also get a lot of traction from VCs, and I think it's important to have more money because we need to go and grow faster in this case if we want to implement our technology. And from this, for sure, we're going to be able to recruit a good team of people to make the fabrication and probably have contracts with telecom providers that basically want to implement QKD channels into their existing classical channels. So that's really the feeling that we got from, for example, Juniper Networks, but also we're talking with Italtel. They want to monitor their classic network, and they don't want to touch anything about quantum. So they want to have a system ready. So for this, we're going to have also to move on the software side by partnering with some people, or we'll see how it's going to go in this case. So here's the team that we have. We are a very technical team. So it's myself. I have a PhD in material science, but I like to say that I'm quantum aware, let's say. There is Piotr Rostowski that is finishing his PhD in quantum photonics. Also Benjamin McClellan that has been very instrumental in developing the first prototype of the interferometer. Robin Elston, that is the head of technician. And Patrick Tang, which is the student from the University of Toronto, which is doing a business student, and is helping us to structure our vision and get some numbers on the market and things like this. So we are now affiliated with Quantum Industry Canada, and we are also pursuing the Creative Destruction Lab, with the last session that's going to happen soon. So we've been invited to the fourth session, and so we'll see how it's going to go from there. So really thank you for your attention, and if you have any questions, you can contact me. But you can also discuss later on, but you can also contact me at this email address, and I would be happy to discuss with you, especially if you want to try the interferometer, and if you have something on to do on the source and things like this. So thank you very much, and yeah, I'm open for discussion now. I can see, sorry, my cam is off, and I try to turn it on and off, but it's not working. So sorry if you don't see me, but okay, you have my picture, so it's enough.
Yes, it's fine. Merci beaucoup, Yoann, pour cette présentation. J'en apprends beaucoup là, sur ce que fait Cryptography Photonics. Donc, je rappelle à tous les participants que vous pouvez soumettre vos questions dans l'onglet Q&A, Question and Answers, à droite de votre écran. Donc, vous pouvez soumettre vos questions en anglais ou en français dans l'onglet. J'ai noté, là, je vois pas de questions pour l'instant. J'ai noté assez tôt dans ta présentation, Yoann, tu parlais d'une vision d'aller vers un quantum supply chain,
Oui.
OEM quantum supply chain. Qu'est-ce que tu peux dire de plus là-dessus?
Ben, en fait, ouais, c'est vraiment ce qu'on a observé quand on a commencé à discuter avec les gens qui voulaient travailler dans le quantum, en fait, c'est qu'ils n'avaient pas vraiment des instruments adaptés pour faire des quantums. Et en fait, ce qu'on a fait aussi, nous, quand on était dans le laboratoire, on avait besoin de sources, on avait besoin d'un interféromètre qui était
Ouais.
adapté pour faire nos mesures. Et donc, en fait, il y a beaucoup de gens qui font ça custom et qui passent beaucoup de temps à développer leurs instruments plutôt que de les acheter directement et donc de passer directement à faire leurs mesures quantiques. Mais on a un petit peu changé notre vision par rapport à ça parce que donc, si on veut se présenter comme un OEM quantique, il faut que le marché soit un petit peu plus mature. On ne veut pas juste avoir des clients comme les universités qui, là, dans ce cas-là, ont vraiment besoin de matériel pour faire de la recherche fondamentale. Ben, mais n'ayant pas un marché quantique assez mature encore, il n'y a pas encore de provider de communication quantique. Et donc, en fait, ce que les gens cherchent, c'est vraiment des systèmes tout prêts déjà. Et même avec les telecom providers, ils ont vraiment besoin ils n'ont pas envie de toucher au quantique. Ils veulent rester dans leur domaine classique et ils veulent qu'on leur donne tout le système quantique et qu'ils puissent interagir justement avec leur réseau classique de communication. Donc, il y a tous des normes de communication entre le channel, le quantum channel et le classical channel ça va être challenging, on va dire.
Oui, ben c'est ça. Ben, c'était peut-être une autre question aussi. Tu touches une autre question qui me touche, fait que peut-être que je vais m'avancer tout de suite dans cette direction-là aussi. Ça m'étonne un peu de voir des telecom providers comme AT&T puis British Telecom se lancer directement là-dedans. Peut-être des bureaux de recherche dans ces providers-là, mais effectivement, c'est plutôt les télécommunications est un marché vertical. Les providers vont acheter à Cisco ou d'autres équipementiers qui font l'appareil. Fait que, donc, la façon que je le vois, c'est que vous faites peut-être des sous-systèmes ou des devices. À quel point il faut aller loin sur des systèmes complets là, de solutions end-to-end, là, de cryptographie quantique qu'un provider pourrait installer dans son système.
Ben, ça dépend un petit peu des clients. Comme je disais, là, il y a AT&T et BT qui font vraiment des tests. C'est vraiment encore au niveau de la recherche. Mais il y a des providers comme Juniper Networks qui qui, eux, ont vraiment besoin d'un système complet. Donc, ça dépend vraiment des clients et de tout le monde, en fait. Donc, il faut s'adapter au maximum, en fait.
Oui, effectivement. Bon, OK, merci. Entre-temps, on a d'autres questions qui sont rentrées. Donc, on a une question de Niaxam. Bon, premièrement, des félicitations sur une bonne présentation. Et puis, qui va en savoir un petit peu plus sur comment la technologie de Key3 Photonics est unique et la situation pour les brevets. Avez-vous une protection avec les brevets?
Donc oui, tout ça, ça a été développé à l'université, en fait, donc à l'INRS, donc groupe du professeur Morandotti. Donc on a réussi à déposer des brevets, que ce soit pour l'interféromètre ou pour la source. Et on a conclu un accord avec l'INRS pour pouvoir avoir une option de licence exclusive et pour pouvoir tester le marché, en fait. Donc, on a nos prototypes, on a notre brevet qui est en place et grâce à l'accord qu'on a avec l'université, en fait, on peut tester le marché, vendre quelques unités et puis après, à partir de là, on va pouvoir discuter une option de licence, une licence exclusive et après, pourquoi pas racheter directement le brevet si la compagnie est assez grosse parce que l'université, en fait, ce qu'elle veut, c'est d'une, essayer d'aider la compagnie, mais deux, être sûr qu'ils vont pas perdre le brevet. Donc, si la compagnie rachète le brevet et qu'elle meurt dans 5 ans, le brevet va partir un petit peu comme ça dans la nature. Donc, ils veulent être sûrs de ça, mais on fait en sorte que la compagnie grossisse et de montrer les bons résultats à l'INRS pour, j'espère, pouvoir acheter le brevet quand on aura assez d'argent, en fait.
Oui, c'est une bonne stratégie. Une question de Benjamin aussi qui demande si Key3 Photonics veut aussi développer les autres composants pour tout un système de communication quantique, incluant l'encodage, le décodage, la détection des photons et tout ça. Est-ce que ça vous intéresse ou bien c'est plutôt l'aspect sur les dispositifs ou sous-systèmes?
Non, c'est quelque chose qui nous intéresse beaucoup, effectivement. Aussi, justement, pour la détection de photons. Je sais que Benjamin travaille là-dessus à l'INRS. Donc, c'est quelque chose qu'on aimerait bien, justement, pouvoir intégrer dans une solution complète. Et aussi, on va essayer d'établir des relations avec les compagnies qui sont plus dans le hardware, dans le software, pardon, pour pouvoir nous aider justement et essayer d'avoir une solution complète avec ça et puis aller voir les telecom providers en leur disant, regardez, moi j'ai le hardware, il y a l'autre compagnie ici qui a le software, on travaille ensemble tous les deux et ensemble on vous promet une solution adaptée à votre réseau.
OK, très bien. Une question, très bonne question aussi de Denis Axam. Dans quelle mesure un réseau de communication quantique expérimental, un testbed de communication quantique au Québec, pourrait accélérer le développement de vos produits et solutions?
Alors, c'est sûr que ça accélérerait beaucoup s'il y avait quelque chose qui se passait au Québec. J'avais cru entendre qu'il y avait Hydro-Québec qui voulait justement faire quelque chose. Je crois que le projet est un petit peu au point mort ou alors j'ai pas beaucoup d'infos là-dessus. C'est vrai que des fois, je suis un petit peu déçu de voir qu'au Canada, on est un peu plus lent par rapport aux États-Unis où je vois que l'US Air Force Research Lab est déjà en train de nous contacter, qui voulait déjà avoir des agreements. Donc, ouais, c'est un peu dommage. C'est un peu plus lent au Québec et au Canada. Mais
oui, un peu plus lent. On n'a pas une nouvelle.
Je sais que ça se fait. C'est dans les tuyaux. Mais voilà. On attend que tout le monde se bouge un peu.
Ouais, ben je pense que ça va débloquer très rapidement. Moi, si j'entends des choses extrêmement positives là, sur un testbed au Québec, oui, il y a d'autres au Québec qui a montré de l'intérêt il y a plusieurs années. Mais là, tout dernièrement, on sent un bouillonnement d'intérêt qui font que on pourrait être surpris d'une annonce dans l'année qui vient d'un projet majeur au Québec. Donc,
je pense que c'est vraiment qu'il faut vraiment inclure tout l'écosystème qu'il y a au Québec, que ce soit les grosses compagnies, mais aussi les startups, parce que je pense que, je veux dire, c'est difficile de faire du quantique si on n'a pas les startups à haute technologie. C'est bien ce qu'on voit avec le vaccin Pfizer. S'ils n'avaient pas fait leur recherche avec BioNTech, ils n'auraient pas eu un vaccin pour la COVID. Donc c'est un peu dans ce sens-là. Je veux dire, Bell voudrait avoir peut-être un réseau de communication quantique. Il va peut-être falloir qu'ils travaillent avec ISEQ Photonics pour pouvoir faire leur réseau.
OK, ouais, message reçu. Le message va être envoyé. C'est ça. Puis un autre commentaire de Denis qui dit qu'il y avait des dollars prévus dans le plan budgétaire. Effectivement, au Québec, le gouvernement du Québec a déposé un budget la semaine dernière. On a des enveloppes. Évidemment, quand on regarde le budget, 500 pages de budget, il y a une ligne quantique. Là, c'est encore un petit peu ambigu, mais on voit des dizaines de millions potentiellement investis dès cette année en technologie quantique au Québec. Je pense qu'il se passe quelque chose.
Oui, il y a déjà beaucoup des projets de recherche et de possibilités de financement avec les projets de recherche, comme j'ai indiqué là. Ça pousse beaucoup au Québec, effectivement.
OK. Donc, un des messages qu'on entend de ta part, c'est un testbed au Québec. Il y a un grand besoin pour ça.
Je pense, oui.
Parfait. Est-ce qu'on a d'autres questions de l'assistance? Alors, si on arrive à court de questions, je remercie encore une fois Yoann, puis merci tout le monde, à tous les participants d'avoir assisté à cette deuxième événement, la perspective Quantum. Gardez l'œil ouvert, il y en a plusieurs autres prévus dans les semaines qui viennent. Donc, la série continue pendant toute cette période d'hiver et de printemps. Et je vous invite aussi à rester si vous voulez discuter avec d'autres collègues que vous avez croisés avant qu'on commence la présentation. Si vous voulez discuter avec Yoann ou d'autres personnes, la plateforme Remo va rester active encore tout de suite après. Donc, sur ce, je salue tout le monde et à la prochaine.
Merci à tous.
Merci Yoann.